Hi there, my name is Graham Jackson and I'm an engineering specialist here at MapleSoft. And today I want to talk a little bit about digital twin for virtual commissioning. So why do we care about virtual commissioning? Well, it all comes down to the cost of design changes. The graph here is sort of a made-up set of numbers. You can associate them to your own company, but the idea behind it is that as you get farther along the design process, you get to the prototyping and product design, it gets more and more expensive, probably exponentially so, to make changes to that design because you've got to go all the way back doing a lot of rework in that process. And if you send a product to market and there's an issue, you might be facing a shutdown or even a recall to deal with. Typically, a lot of these problems start coming in during the commissioning phase when you're actually starting to put things together. Your controller code, so attaching it up to the physical system, you're building prototypes. That's where you start to see, this motor isn't quite powerful enough, or man, there's a glitch in how this controller is responding to that input. The key idea behind virtual commissioning is that it allows you to start identifying these problems earlier. And of course, earlier means it's less expensive to make changes when you find those problems. Now, it's not just about money, and I should say that these techniques have been going on in aerospace and automotive for a long time. Research actually shows that doing some more of this work up front can save you dramatically in the long run. And it's not just about that money, it's the cost of rework, but also the cost of over-engineering. Either your margins are thinner since you're using bigger motors than you intended, or you're pricing yourself out of certain competitive deals because you're just not sure that you've correctly gauged the dynamics of your system. There's of course damaged reputation if you send something out and there's a failure. And if there's a window of time that you're trying to hit, it's much less predictable to get there because you don't know how long that integration phase is really going to take. What do I mean by digital twin? Well, digital twin is just a virtual representation of a corresponding physical product. When I'm talking about digital twin, I'm not talking about the version that comes from this bank of data that you use machine learning to gauge behavior. I'm talking about the digital twin that's built from physics-based models. And the advantage here is that you don't need a prototype to start using the digital twin. You can use it as early as the conceptual development phase. You could play with it before anything is actually even built. Of course, it works well with virtual commissioning, but even after the fact, you can actually have these models running online after production to help with diagnostics and operations. So overall, we hope that they will bring you smarter designs. And of course, these are the models that you put together for the virtual commissioning process. So in a nutshell, this is when you take these virtual models and you connect them to your virtual PLC. So you can do all this testing of your PLC and control with the real virtual system before you ever hook it up to a physical prototype or download that PLC code to a physical PLC. So that's virtual commissioning in a nutshell. And that's the thing that we're talking about, to sort of save and find those design failures and integration problems earlier in the build phase. So let's go into virtual commissioning just a bit more. It starts off in the conceptual phase. You can go through rapid iterations of the design. A lot of people that we talk to, they use Excel or FEA for this right now, and what they're missing is some of the accelerations and dynamic loading. So this is where the digital twin can be used in the conceptual phase. And of course, you can hook that right into your controller and even perform testing on your PLC code and hardware. And then, the last thing you can do happens actually after you commission your product. You can use it online to help with diagnostics. You can use it inline to avoid adding more expensive physical sensors to your product. There's really a lot of things you can do with these models after the actual commissioning phase.
This is the goal: a digital twin that encapsulates the dynamics of the system, that allows you to test your controller code against a virtual model that represents the real thing. It allows you to investigate questions of vibration, of motor sizing, or even general control strategies before you have to build or possibly rebuild anything. This is what MapleSoft means by virtual commissioning. But how do we get here? We do it by following a well-defined sequence of steps. We've started with your CAD model. Maybe we've used it to grab some inertias, maybe some kinematics, or just the graphics that we want to use for the simulations later on. We've imported it into MapleSim, and now we can hook it up to the other multi-body components within, or the 1D hydraulics to actuate it. For this simple system where we've got a hydraulic actuator moving a platen, we've got some friction acting on a cylinder, we've got a simple hydraulic circuit, and to simplify the control that's going to be happening external to this plant model, I've got a loop going that basically specifies the set point and the motor or the pump speed that's powering this hydraulic circuit. Assuming at this point you've already run a variety of simulations, you're happy with the results, happy with performance, maybe you've done some parameter sweeps where you vary something and sort of see how the design holds up. And at this point, you're ready to export this model and test it against your controller code that's going to be living on the PLC. How do you do that? Well, the first step is to take this model and wrap it in a subsystem in MapleSim. So here I've taken that model, I've put some things that are coming from the outside, so my control signal is a command signal to the directional control valve, and I've got some outputs. These are the things that are either sensor data that's coming out that my controller is going to need, or just things that I'm interested in during the simulation. I confess I've put a fairly simplistic controller here. It's just a PID, and in fact, I've just put a P controller on it. But it's enough or sufficient for us to demonstrate how we can export this plant model and build this up in our PLC. So we're going to take a look at Studio 5000 simulation interface. The first thing we're going to do is load that FMU that we just generated. And now I'm going to load the ACD file that goes along with it. This is my control file, or my PLC, the file that contains the controller code for my PLC. Once that's there, I verify that the communication paths are set up. Specifically, I want to point that to the 6th slot on my virtual PLC here. And then I want to download the program. So this downloads this module to the PLC that I've got, or the control board that I've got. So now that we've got this set up, we can go about connecting the tags. What's really happening here is that we've got a plant model, that's the FMU, that's going to be running alongside the control program in the ACD file. But they have to be able to communicate back and forth, and they do that via tags. So you can select a tag, drag it across, and say this tag from the FMU attaches to this one in the ACD. Now, if you've got a lot of these, it can be quite cumbersome. So there's a nice option here to auto-connect. When you do that, it'll automatically piece all the tags that you see that have the same name to their counterpart in the ACD file. Now, quick pause. If you'll recall, where did these names come from? Take a look at this subsystem that I generated. Command was the input, plant position, pressure A, pressure B, power, and set point. These are identical to the names that you see appearing here as the tags for the FMU. And these are the names that I've then put, to simplify my life, in the ACD file. Once all these things are done, I can go to the Start Simulation tab. And the last piece that I want to do is launch MapleSim Insight. Now, Insight is a tool that's sort of a companion to MapleSim models. When you export an FMU, you can use Insight to basically do the plotting and visualization for that FMU. So it's not just the code that we're going to be running. We're actually going to be able to see this thing running while we go. I'm just going to hide that panel. You can see I'd run and saved or stored off a previous simulation that I'd been doing. Now that that's ready to go, I've loaded it here, and I can hit start. That's going to actually launch the FMU, start it running, as well as start the ACD program running on the PLC. You can see that's up and running here, and if I look over to Insight, I can see the actual motion of the physical plant being controlled by the controller. Now you can see the controller's got some work to do. There's some choppiness here in the response, but that's okay. The whole purpose here is to be doing this testing, to test the system with the dynamics and test out my controller. So I'm actually going to pause the simulation because I know I've got work to do on my controller. And I'm going to go over to Studio 5000 and go online. Now I'm going to need to upload the model. That's fine. It's going to go off and do that. And once it's done, I'm going to actually be able to edit and modify the control code as the system's running and actually see how the response, or see what the response is. But let's go back and start that simulation up again. So we're going to continue the simulation. It's going to keep running. And now I'm going to go here and let's say I've got, maybe my gain is too tight. I'm going to reduce it and see how that affects my system. So now I can come back. You can see that vibration that was happening at the top is greatly reduced. I still have a little bit of wobble here. I've got some work to do on my controller, but it's an improvement from what I had before. And this is the kind of back and forth that you can start doing, playing with your model, once you start using something like Simulation Interface, MapleSim, and its companion app, MapleSim Insight. With these tools, you can start to do virtual commissioning and test your controller code against a plant model with dynamics before you build anything.
A quick example from the machine design world. This has to do with a customer who had a product built and were finding they were getting failures with their motors when they sent the products out. And actually, a deeper analysis after, it showed that they were missing some spikes in the current draws on the motors. They went through their commissioning phase, test cycles, and it all worked out. But after it ran, it failed earlier than what they predicted. It had to do with the fact that they didn't have an accurate enough model of the actual torques that the motors experienced and were required to deal out because they were using just Excel to do this sort of static, steady state analysis. So they just weren't capturing detailed enough accelerations. So by being able to probe that better with our software and to do that testing up front, not only were they able to say, hey, I can just adjust the motion profile, I don't actually need to add a bigger motor, but they were also much more confident that when they sent new products out, that they weren't going to experience the same sort of failures. So I hope that gives you a quick whirlwind tour of virtual commissioning and the kinds of things you can use it for. Really, the nutshell idea here is that you're taking a virtual prototype of your machine, you're hooking it up with the virtual PLC, and you're doing the testing when it's still very inexpensive to make design changes.